All right, so we're going to talk about solutions now. What is a solution? Well, if you'll remember back at the beginning of the year when we talked about the types of matter, solids, liquids, and gases, and then we did talk about the identifying things as either physical or chemical and physical chemical changes, and we talked about solutions being homogeneous, heterogeneous, suspensions, colloids. All right, so we're going to revisit that idea and we're going to go in a little more detail. So solutions are homogeneous mixtures. You can't tell the different parts. So for example, if I had salt, which is the solute, which is the one present in the smallest amount, dissolved in water, which is the solvent, which is present in the larger amount, we would make a saltwater solution. And you'd have ions of sodium floating around and chloride ions floating around in water molecules. And the reason why, and we can talk about colligative properties a little later, but if you'll remember, water is polar and it can dissolve things that are also polar or ionic. Okay? So solutions contain two parts, the solute that gets dissolved or is present in the lesser amount, and it seems to disappear or take on the state of the solvent. The solvent is the substance that does the dissolving or is present in the larger amount. Now, do all solvents have to be water? No. Do all solutes have to be salt? No. You can have a variety of things. It's just in a lot of cases in chemistry, when we talk about solutions, water is the solvent and it's called aqueous. Okay. So when both the solute and the solvent have the same state, the solvent is the component present in the largest amount. Solutions in which solvent is water are called aqueous solutions. And in high school chemistry, general chemistry, that's pretty much about all we use mostly, unless we're studying something special like nonpolar solvents, organic solvents, things like that. So we often refer to water as the universal solvent. Why? Because most things can be dissolved in water. Like dissolves like. Solutions that contain metal solutes and solvents are called alloys, like brass. Alloys like steel. Things like not just brass, but I forgot the other one. Of course, steel is an example. Pewter is another example. Okay. And then brass, what's the other one? Gosh, I can't remember. It doesn't matter. Forget it. Brass and something else. All right. All right, so you can have solvent, iron, and solute, carbon, together make steel. But you got to make it molten, get it pretty hot. You know, it's not liquid at room temperature. It's solid at room temperature. So unlike water, which is a liquid at room temperature. Okay. So there are three types of solutions based on the solvent. A gas and a gas mixture is an example of air. For example, you can have gases dissolved in gases. Liquid and a solid, for example, like Kool-Aid, any kind of your powdered drinks, or if you just make saltwater solution or sugar solution. Liquid and a liquid, such as rubbing alcohol, beer. Rubbing alcohol is really like a 70% isopropyl alcohol mixed in water. Liquid and a gas, like as in soda or any kind of soda pop, because carbon dioxide at low temperatures and high pressures can be dissolved in liquid, especially water, like as in sugar water, like as in Coke. And you can take the carbon dioxide, which gives it its fizz, and dissolve it. And then a solid and a solid, such as in brass. When one substance dissolves easily into another, it's said to be soluble. Salt is soluble in water. It doesn't change the chemical makeup of anything. It just makes it dissolve. So it doesn't change salt properties. It's just ions of salt in water and doesn't change the properties of the water. We could physically remove them. So this is a physical process, not a chemical change. Okay. So it's said to be soluble. Oil is soluble in gasoline because gasoline is nonpolar. Oil is nonpolar. The idea of like dissolving like is how this works. Okay. So vegetable oil can be added to gasoline to make diesel fuel. And of course, You've probably heard about these, reusing cooking oils in combustion engines, and you can retrofit them so that you can actually use them. So they can actually come and take like the fry oil from Burger King and places like that. So there's usually a limit to the solubility of one substance in another. And what do you think those are dependent upon? Temperature and concentration. Yeah. Okay. When one substance does not dissolve into another, the two are said to be insoluble. So like oil and water. You know that. You've heard that term before. More specifically, when two liquids are soluble in one another, they are said to be miscible. So we can also say, when they're soluble, they're miscible is the special like sciencey term for it. Or when they're not soluble or insoluble, we can say they're immiscible. So those are the alternative words for soluble and insoluble, miscible and immiscible. So why do water and alcohol mix or dissolve well in one another? Well, remember, water is slightly polar. Alcohol is also slightly polar. So these slight charges attract each other and engage in a physical bond. In particular, it's known as a hydrogen bond. When these two liquids dissolve well in another or are miscible in one another. We'll talk a little bit more about these intramolecular forces later. So you can have these polar bonds of ethanol, which is this CCOH, and it can be positive here with the H and more negative around the oxygen, less so with the carbons. These are more equally shared. This is where the polarizing area is of this compound, this molecule. And again, the oxygen is being more electronegative, therefore it is attracted to the hydrogen. And as a result, you'll end up with a missing, a bonding which helps to dissolve one inside the other. So these two liquids are immiscible in one another. Water has a slight charge, oil does not. Note that all of the water molecules have a slight charge, whereas oil is this saturated, most, and it can be unsaturated too, but most are saturated and there's no polar negative or positive to help break up the molecule size. So instead, they just all form these hydrogen bonds with each other. Molecules that are similar in structure tend to form solutions. Like dissolve like is what we typically say. The solubility of the solute of the solvent depends on temperature. Solubility is the measured amount of solute that can be dissolved in a given amount of solvent at a particular temperature. Solution that contains very little solute and a given amount of solvent is unsaturated or dilute. A solution that contains the maximum amount of solute and a given amount of solute at a particular temperature is said to be saturated. And a solution that contains more than the maximum amount at a given solvent at a given temperature is supersaturated. So you can see some examples here with like dye and like sugar and candy and like sugar and honey are examples of supersaturated. And that's how you make the little rock candy crystals, is you have to make a supersaturated sugar solution. Solids increase their solubility in water as temperature increases. And we'll talk a little bit about that later on. That has to do with colligative properties. You increase the kinetic energy of things. They bump into each other more often, more frequently. As a result, when they collide, they can dissolve easier. And there's some other things that help things dissolve better too. Okay. But increasing temperature is one way to increase the solubility of things. So you can see here from this little chart, you can start off with like sodium nitrate is pretty soluble at 0, and then it greatly increases its solubility. And this is like 90 grams and 100 grams of water, which is like 100 milliliters of water. And then you can increase the temperature up to 30, and of course we could extrapolate this out if we wanted to. Same thing with calcium chloride. It's pretty soluble at lower temperatures, but then also greatly increases its solubility as you increase temperature. But whereas like potassium chlorate has a pretty low solubility at these lower temperatures, and it's really not going to improve until you get to around 100 degrees Celsius. Okay, so same thing with potassium nitrate, pretty low solubility at low temperatures, but greatly increases. And then look at sodium chloride. It's pretty stable with its solubility across most temperatures. Okay, so anything below for like potassium chlorate is said to be unsaturated. Anything on the line is at equilibrium and is said to be saturated. And anything above the line is said to be supersaturated. More sugar can be dissolved in water at higher temperatures. This is how you make candy. This is why you heat the water when you stir it. Both the heating and the stirring help increase the solubility. Whereas if you put you're making your iced tea, a lot of times if you boil your water to make your iced tea and then dump your sugar in, your sugar will dissolve. Versus if you ask for iced tea that's not sweet and you add your own sugar, what happens to the sugar? It falls to the bottom, doesn't it? Yeah. So all candy is an example of a supersaturated solution of sugar and water. So let's estimate the amount of potassium chloride that can be dissolved in 200 grams of water at 70 degrees Celsius. So we're going to look at potassium chlorate, 70 degrees Celsius. Interpolating from the graph, if we observe potassium chlorate at 70 degrees Celsius, it appears that 30 grams can be dissolved in 100 grams at 70. So therefore, if we had 200 grams, we would be able to dissolve 60 because it's going to be the 30 for every 100 at 70. So if we had 200, it would be 60, twice as much. So there's lots of different kinds of questions you could ask from these kinds of graphs. Okay. So not just directly, but also inferencing from the graph directly. Gases decrease their solubility as the temperature increases. So solids increase solubility as temperature increases. Gases, and you know this, you leave your hot Coke out opened, what happens to that carbon dioxide? It goes away and your soda pop goes flat, doesn't it? Yep. So cold soda is bubbly because the gases have a higher solubility at low temperature because their movement is slower, therefore they get more condensed, therefore they have less kinetic energy. Okay, then they're going to be under pressure, and then when you release that pressure, that's why it goes psst when you open it, and that's why warm soda is flat. Yuck. So gases decrease their solubility as temperature increases. As the temperature of a solution increases, so does the added kinetic energy to the gas molecules trapped in the solution. Therefore, the gas moves faster and the intermolecular or physical bonds they have formed will break and more of the gas molecules escape in the solution phase and transition to the gas phase. So let's look at this. Fish need oxygen to breathe, right? So this is important to know in terms of like environmental type science stuff. Oxygen dissolves in water and fish extract the oxygen using their gills. So there's dissolved oxygen in water for fish to breathe. They don't just go up to the surface and glurp air, okay? So based on the graph to the left, what would happen if the amount of oxygen or O2 present in a lake with a factory leads warm water into the lake? So there are some lakes that are created to cool nuclear plants or coal burning plants, and then that warm water is actually released back into the lake. So think about that. Where do you think you're going to find the most fish? Nearest where the effluent is or furthest away? Well, which effect could this have on the fish living in a lake? Well, it would decrease the population because as long as you have warm water, the molecules of oxygen can escape from the liquid phase to the gas phase, and as a result depletes the oxygen and kills the fish. Sad fish. Bye-bye.